Our department is one of the 6 technical departments of the Faculty of Mechanical Engineering in the University of West Bohemia in Czech Republic. Departments include of two sessions, the fluid mechanics and thermodynamics session, and the second, the heat, nuclear, and alternative devices. And our activity corresponds with these two sessions. We can make the short list of our main activities. Generally, we can say that we focus on the increasing efficiency and reliability of energy machines and device. One of the important activities is developing the heat exchanger for Gen 4 reactors, and the molten salts reactor cleaning, the gas separator. The next heat exchange intensification with the gas lift method. That's what I will present today. Then the research on the turbo machinery, research of my colleague on redefinition of the accident with the coolant loss, what we call the big loca type, determination of the method of the seismicity hazard of the selected location, the blade and tube vibration and the turbo machinery, and the last but not least the activities, cooperation with the Škoda company is the burn fuel containers, especially the heat removal from this new type of the containers. There is the several different devices installed at our laboratory, for example, transonic and supersonic aerodynamic tunnel, the water, molten salts and gas loops, experimental gas turbines and experimental air turbines, axial compressor ventilators, etc. The introduction to the gas lift. In fact, what is it, gas lift? This is the known effect, known phenomena, which was used on the middle of on the middle of the 8th century in the Chemnitz for the mining. It still is used. We recognize two types of the gas lift: the continual delivery of the gas into the flow, and the second, the periodical injection of the gas, which is more important for the mining. For us, is much more important the continuous gas delivery method because we need the homogeneous the flux. We can imagine to use as the gas helium, in fact, because we can use the helium for cleaning molten salts from the gaseous fission products, what we call xenon fission product poisoning. We can divide it the two phases flow to the several types described on the presented map. This is presented by the author title. On the axis, you can see superficial velocity. On the X is for the gas, and Y is for liquid. And we recognize the several types. For example, the slug is important for the mining, and for us is much more important dispersed the bubble flow. Why? Because the flux is practically homogeneous. The flux include the small droplets, and the speed of the liquid phase is nearly the same like the gas phase. Then we can say that the gap slip ratio is close to the 1. On the literature, you can find the different the maps as I present, for example, from author Hassan and Kabir, or from author Kai. Is the similar. And also we recognize this map for vertical and horizontal flow. The types of the two phases flow. The first one, the bubble flow. Imagine the blue is the liquid, the white is the gas. The liquid include the small the bubbles, nearly homogeneous the flux. The second one, which we call slug or plug flow, is for this is typical the big the bubbles which transport the part of the liquid. That's why is used for the mining. Then the typical is churn flow. This is transient between flux and annular flow. The annular flow for this is typical the liquid film on the wall with the air core, and this core can be with or without the small droplets. And then the other is with annular flow. It's also transient. This part is missing, but in fact this is the same, but reverse with the bubble flow. The gas is everywhere and transport the small droplets opposite. It's probably too much technical details for this conference. I will jump. I just want to present that we are able, for very simple model, find the hydraulic losses, analytically predict. We are able to calculate the mass flow cross-section medium density. What we need, we are able to predict the mass flow rate for natural convection. This slide shows us what is important for us is the increasing of the velocity by gas lift phenomena, and we need also the velocity for the gas phases. That's what the slides show us. Well, because I'm teacher, I have to show this very general slide just to describe what we do. Well, if we want to describe some real phenomena, first we have to select important the properties. The picture shows us two ways. The right is the numerical way. For this, I have to define the physical model. In our case, this is the two phases flow, turbulent flow. Then using conservation laws of the mass, energy, momentum, etc., we obtain the mathematical model. In our case, this is the system of Navier-Stokes equations spread with equations, the state equations for ideal gas, equations for turbulent transport equations, etc. By discretization, we obtain the numerical model. This is system of nonlinear algebraic equations, and using some CFD solver, we obtain the variables which describe our real phenomena. The second way, what I present here, is the experimental way that we decided to design and construct some experimental device, provide the experimental modeling, and obtain the variables with this experimental way. Of course, the validation and verification is necessary. Our model corresponds with this very simplified scheme of the primary circuit, which consists of the active zone. After the crossing through tractive cylinder is number 3. There is input, the gas input, the cylinder, then the volume compensator with the free surface, the heat exchanger, and the cold length. This is now the scheme and picture of our demonstrator, what we call demonstrator of two phases flow. As I said before, consists of the model of the active zone with the electric heating, input the gas, the cylinder, the volume compensator, the heat exchanger, and the cold leg. Of course, in this demonstrator, we just use the water and gas for two phases flow demonstration. and some part is prepared for the PIV measurement. Just details of the gas input, we are able by the changeable nozzle to control the size of the gas bubbles in the input. The list of the variables which we have to measure to describing the real phenomena, we have to measure pressure, measure temperature, velocity field for both phases, for water and for air, mass flow for both phases, distribution of the bubbles and the size of the bubbles to understand which type of the two flow phenomena we observe. And now I briefly to describe our measurement technique which we used for the mapping velocity field and the bubbles size and distribution of the air is useful to use, for example, PAV method. This is optical method. Generally consists of the double pulsed Andeak laser produce two beam of the laser on the giving the time by optic is spread to light sheet on the target area. This is the area of the flow. This target area is saved by CCD camera to the two pictures, and by the mathematical procedure we obtain the information about flow field. You see that for this visualization we need the optical access for camera and also for laser, and we need the particles, because in fact we make the photos of the particle position, and from this position by the correlation we obtain the information about velocity. And also you can see that in fact we are able to measure just the velocity components lying on the light sheet. There is several modification of this optic method. One of this which we call stereo PIV or 3D PIV. Using two cameras on the different position and very complex calibration, we can obtain the information about all three the components of the velocity. I mentioned before the data analysis from particle image velocimetry. We have two pictures with the particles position using fast Fourier transformation and autocorrelation. After some filtering and inverse Fourier transformation, we obtain correlation peak, and this peak gives us information about probable velocity field. Other modification of this optical method useful for two-phase flow is interferometric verification. Using two camera, one camera is focused on the target plane, the second is unfocused. And in fact, the number, then we can see the interferometric line, and the number of this line correspond with the size of the bubble. Of course, there are lots of limits for this method. For example, the bubble must be spherical. The dynamic of this measurement must be less than 20. It means the ratio between the bigger and smallest the bubbles, etc. The next modification of PIV is laser with the fluorescence method. We bring the fluorescence particles or the liquid which we call rhodamine. We use two camera, one camera with the filter. the rhodamine absorbs the light from the laser on the wavelengths 532 and emits with the higher wavelengths, which is the sensitive, the second camera with the filtering. Then we can recognize Bose phases. We can recognize the gas phase from the liquid phase. Using rhodamine is also possible to measure velocity field because the light is sensitive on the temperature or concentration. Well, also the very complex calibration is necessary for this method. The next method which we use is ultrasound velocimetry. Doppler velocimetry is the principle is known. In fact, both this acoustic method and the PIV method, is the optic method, need the particles. Unfortunately, both methods need the different particles, is the different size and different properties. But we are able to use one particles for both method. This is not optimal case, but it works well. Much more details I will publish in next year in Paris conference, the Fast Reactors conference in May. And for temperature measurement, we use the classical thermocoupled and for pressure measurement, the pressure. And now let me present some typical results. This slide shows us the case without gas lift. This is just natural convection. On the left top, you see the velocity flow depends on the time. On the bottom, you see in the transient the moment when you switch on the heating on the device. Here you can see the temperature when you change the power of the heating, and the last picture shows us the velocity profile, typical turbulent velocity profile. The similar we can obtain for the gas lift phenomena, the velocity profile across the cylinder, the graph, the velocity, water flow rate depends on the airflow rate which we bring for different the size of the bubbles in input. That's the three pictures for different pressure in the reservoir. Maybe little comments for velocity profile. You can see that we have the problem with the symmetry, and in fact this picture shows us that our distribution of the gas is not perfect, and we deform the velocity profile. It was the information for us that we have to improve the gas input. Because we use the camera for PIV, we are able to make the photos of the distribution of the bubbles, so we can compare this different mass flow and different, maybe the next picture, different size of the bubble on the inlet. But this is not picture for PIV. This is just visualization two phases flow. Well, conclusions. We can say we are able to measure two phases flow. We are able to control the size of the bubbles on input. We have to improve measurement. We have to improve the gas input to obtain the homogeneous input. We plan to measure together with both the method, measure precisely the size of the bubbles and velocity of the bubbles, etc. That's all. This is contact at myself and my department, and thank you very much for your attention.
You have established a laboratory scale of measurement of the two phases flow and the velocity, field, and the temperature. So as far as I know, that the molten salt itself is transparent, and when it's molten. And what's your opinion about the the large scale monitoring of the high temperature loop? Do you have developed a roadmap for that?
I can imagine the experiment like this, but understand why we construct the small device with this diameter and with this temperature, because we are limited by the material for this moment. And of course, there are some similarity in fluid mechanics that we can use our knowledge from this experiment for molten salts with helium behavior. Okay, if I will construct the loop with the molten salts, probably I will lose the optical access, that I will be not able to use PAV method anymore. But there are some other measurement techniques like tomograph techniques, which we have and we use for other application. So this is the limited, in fact, temperature is limited by using the materials, the glass, plexiglass, just to see inside and to measure velocity field.
Thank you for the nice presentation. With regarding to the bubble size, I have a question that in your experiment, what's the bubble size range? And how do you control the bubble size?
We are able to control just on the beginning the bubble size on the input. They correspond with the changeable the nozzle, and on the results you see that we tested for this case from 0.5 millimeter up to 7 millimeters, and for these results you can see some significant difference. But this is because we are not on the good type of the two phases flow, what I mentioned in the beginning. Yeah. Yeah, that is important to increase the pressure of the gas to move to be on this type, disperse the bubbles type of the two flow.